Hello, so welcome to the Lewis diagram video. So today I'm going to go through how to draw Lewis diagrams of simple molecules and how to think about their shape. So we're only going to do the very simple shapes, and then you can even start thinking about how the polarity of that molecule will be. So let's start off with a very simple compound. We'll start off with F2. So this is when you've got two fluorines that come together and they're covalently bonded. So they're two nonmetals, so we know nonmetals make covalent bonds, and nonmetal and a metal will make an ionic bond. So covalent bonds are when we share the electrons. Now the sharing of those electrons are the outer shell electrons. They're able to interact with other atoms or molecules that are around. So in order to work out the Lewis diagram, we firstly want to think about what valence electrons will exist in the fluorine molecules. So each fluorine, if you look it up on your periodic table, has 7 valence electrons. So you're counting from that second period and you count all the elements across till you get to fluorine and you'll get to 7. Now we've got 2 of those fluorines, so we're going to be adding another 7. So 7 for the first fluorine, 7 for the second fluorine. And that will give us 14 electrons in total. Now, when you write your Lewis diagrams, the first thing you want to do is draw out your 2 atoms with a covalent bond between them. Remember, a single bond has 2 electrons, a double bond will have 4 electrons, and a triple bond will have 6 electrons. So in doing this, we've used 2 electrons already. So we have 12 electrons left over to satisfy this molecule. So we follow the octet or the duet rule. There are some differences where you don't need to follow these, and these are boron and beryllium. So those 2 elements, boron and beryllium, can have less than 8 electrons. It's got to do with the structure of the atoms. And if you've got a larger atom that has the d orbitals available, so thinking of your p block, think of aluminium down, they've got the d orbitals available. They can hold more than 8 electrons if they need to. So they won't choose to, but if they need to, they can keep this molecule stable. So fluorine is just in that second period. It doesn't have the D block, so this one would be going, each of these atoms, for 8 electrons. So we've got 12 electrons left. So I'm going to draw big X's. You might use dots, but just to keep it really clear, I'm going to do X's to represent electrons. I'm going to draw them together in pairs because they sit in pairs in their orbitals. So let's look at this fluorine here. We've got 2 electrons that it owns from, or that it shares from this shared bond. So we've got 2, 4, 5, 6, 7, 8. So it's got 8 electrons. I've drawn 2, 4, 6 extra to get to 8. So if I subtract that from my tally, I've got 8 electrons left over to try and make the other fluorine. Sorry, I've got 6 electrons left over to try and make that other fluorine have 8. So if I've got those on there, I've used them up. And I look at these 2 atoms and I check to see if they've got an octet. So we've got this fluorine, we've got 2, 4, 6, and it's got a share of these 2, so we can count these as well. So 2, 4, 6, 8, so it's good, it's happy. This one here, we've got 2, 4, 6, 8. So this one's happy too. So that's got a satisfied Lewis diagram. Now, when there's 2 atoms joined together, they are linear. And because they're exactly the same atom, the polarity of this particular molecule would be non-polar. So it's a tug-of-war situation. Fluorine has the most ability to pull electrons onto itself out of any of the other atoms. It's the most electronegative. And because they're completely linear, if they're pulling the same strength, they're going to completely cancel out. So they're non-polar. So let's try something a little bit more complicated. So let's have a go at doing CO2. So thinking about those valence electrons that exist on this atom. So the first atom would be carbon. So if you count across, you get 4 on carbon. So again, that's in the second period. And if you count from the first element in that period along to carbon, you'll count up to 4. And then if we look at oxygen, you should get 6. And we've got 2 of those. So we've got 4 plus 6 plus 6, giving us a total of giving us a total of 16. So 12 plus 4 is 16 electrons. So E minus is just my representation of electrons. So first thing I do is I write out my carbon, and we know it's going to be bonded to the 2 oxygens. So you may have the carbon underlined in the question to indicate it's the central atom, or you may be told that in the question. So in drawing these 2 lines, I've used up 4 electrons. So I've got 12 electrons left over now. So what I want to do is, because I have a central atom and outside atoms, I want to fill up my outside atoms to reach their octet first, and then I want to try and work on the central one. So I've got 2 on this oxygen, so 2 that are shared. So if I put another 6, I've got 2, 4, 6, 8. Now I don't have many electrons left over, but we'll play out in the way that we did before. So subtract that 8. I've got 4 left over. Put on my last 4 on the other outer atom. And then I go to count it and I go 2, 4, 6. I don't have enough. So what can I do? So what I can do is go back and check my calculations, because I've obviously made a mistake. And I've just noticed that 12 minus 8, I didn't put 8 on there, I put 2, 4, 6. So let me fix up my calculations and then we'll continue on. So this is why it's always good to have a running tally in the corner. So minus 6 gives me 6 electrons. Now that makes more sense. So I've got 2, 4, and I've got 6 there. I've used them up. So now I'm down to 0 electrons. And now looking at this, I can see that this has 8, and my central one, my carbon, has 2, 4. Now what I can do is, because it's electron deficient, I can move electrons from the ownership lone pair kind of domain on the oxygen and move them into the sharing region in between those 2 atoms. So they can both get a share of those electrons, rather than having specific ownership only onto that oxygen when we have them drawn as lone pairs. So let's remove these and move them into the center. So now carbon's got 2, 4, 6. So I'll do the same for the other side. Okay, so now I've got carbon, 2, 4, 6, 8, 8 electrons, perfect. Oxygen, 2, 4, 6, 8. Oxygen, 2, 4, 6, 8. So they've all got their 8 electrons now. So after we draw our Lewis diagrams, we want to think about the shape of that. Okay, so carbon has no lone pairs on it. It's just got 2 bonding atoms coming from that. So when you have that structure of just 3 atoms bonded together, you'll get a linear again. Now, because this is linear, the atoms on either side are exactly the same. There's going to be no polarity, so it'll be non-polar. So it's the same sort of rationale as we had with the F2 as the CO2 does. Okay, so I'm going to try one more example. And let me draw it up. So this next one I've chosen is charged. So CO3, 2 minus, and carbon's the central one for this one. So looking up those valence electrons, so that's second period again, we've got 4 for carbon, and oxygen has 6. And we've got 3 of those, so I'll just use a multiplication. And then we've got this 2 minus that's on the molecule. So that means it's got 2 extra electrons. So I'm going to write 2 E minus there, so you can see where that's come from. So that 2 minus is added in. Now, if I have a positive, then I'm going to be subtracting 1 electron. If I have a 2 positive, I'm going to be subtracting 2 electrons from my total electron count. So this is distributed over the whole molecule. So if we add that up, we get 24 electrons. So I'll start drawing it. So carbon in the middle. We know there's going to be 1 oxygen on each. We're going to have 3 oxygens coming off that central carbon. So we've used 2, 4, 6. So we go to 18 electrons. Now this is charged, so I need to put square brackets and put the charge on the outside. So this is indicating that there's got that 2 extra electrons there. Now fill up the outside atoms and work your way into the center. So 2, 4, 6. It's got 2 there, so it makes it 8. So I've subtracted 6, 12 left over. 6 left over. So now I've used up all of my electrons. So my outer oxygens, 2, 4, 6, 8 each, because they've got those sharing ones. But my central carbon only has 2, 4, 6 electrons. So what it wants to do is want us to have 2 more so that it can be stable. So we can share a lone pair from each one of these oxygens. So it doesn't matter which one you choose. Let's just choose the bottom one. So rub out its lone pair from its ownership domain, if you want to think of it like that, into its sharing part. So it's now sharing that lone pair, and carbon has 2, 4, 6, 8 electrons now. So it could be any one of those oxygens. I've just randomly chosen the bottom one. And this is kind of when we go into that delocalized model on how these structures exist. So we're just kind of looking for the localized. Now they're actually, if you draw it out for each option that you could make, that would be your resonance structures for this particular compound. So there would be 3 possible resonance structures. It might be a double bond between this one, double bond here, or a double bond here. Each one of those would be different Lewis models. So the next thing we looked at was the shape. So if you've got a central one and 3 bonding, and there's no lone pair on that central one, then it's trigonal planar. And because it's charged, it would be considered a charged species, which would be water soluble. So you can then kind of say, well, it's probably, if it's soluble in water and water's polar, then this would be polar. So because it's water soluble, you could say this is polar. So any compound that's charged would be a polar compound. Okay, so hopefully that helped you in understanding your localized electron models, so your Lewis diagrams, predicting the shape, so very basically, and a very basic introduction on the polarity of those compounds.